Howdy, and the next teacher that I want to appreciate for Teacher Appreciation Week is Mr. Dan Teague, or actually he's Dr. Dan Teague now. He got his doctorate after I left NCSSM, and that's the North Carolina School of Science and Math. I had a lot of excellent teachers at NCSSM. In my earlier video, I talked about my favorite teacher of all time, Dr. John Kalina, who's in physics, and Mr. Teague was a math teacher, and in this case, it was for a specific class he taught. Again, it's not how he taught things, it was what he taught, because this class opened my eyes to use of math that I was not familiar with, and it's basically been my career, undergraduate through graduate, through what I actually make money doing, and that's applied mathematics. I don't remember the exact name of the class, and here I'm just going to quickly show you the math department at NCSSM. Click on the courses. Let's see what courses they have. And I don't know if they have this anymore. It's been over 25 years since I've been there. So let's see what they have. Research. Oh, this is everything. So Department of Mathematics. I don't know if they're going to have the courses. I'll edit this out. Okay, so it looks like they have definitely moved on since I was there. I'm seeing they have numerical analysis, they have modeling with differential equations. I didn't get to do this stuff until I got to college. At the time I went, there weren't a lot of students who had taken calculus before they had gotten there. I actually ran into trouble and ran out of math classes by the second semester of my senior year. And part of the issue is you have to take a math class every semester. So that caused trouble for me. Well, the course that Mr. Teague taught was, I think it was called math modeling. Maybe it was math modeling with pre-calculus or something like that. But it wasn't really pre-calculus modeling. Most of it was what I would call discrete math. We had some graph theory, if I remember correctly. There were some optimization problems. It was not necessarily finite math. And we got to try some very classic optimization problems and some other math modeling problems. But we also got to participate in a math modeling competition by COMAP, and I think it's been supplanted by something else. And I'll talk about that competition in a moment. But we also got to do a final project, and the project I did was modeling the Electoral College. I started in, I guess it was, it's the first election, 1796, I believe, or maybe it was 1792, well, 1792 or 1796, either way. I modeled certain metrics with regards to, or tried to measure the decision power, as it were, of different states. We already know the Electoral College has some really interesting results given the way most electoral votes currently are granted. It's state by state as an entire block. And there's some interesting dynamics with that. I wrote a program to go through the various combinations, but I basically had to stop around 1820 because there were too many states at that point for me to actually do a direct calculation. If I remember correctly, they either use sampling approaches or approximation approaches to do this currently, if anyone's going to do it, to try to measure the power in such a block voting situation. It's not block voting anymore. It was funny because I get to 1820 and then I'm trying to do 1824, I believe, and I'm realizing I'm not getting any results. And so I do a little bit of timing or clock on my algorithm, and I try to figure out how long it will take my my program to run through 1988. And if I remember correctly, I calculated it would take at least a couple thousand years for it to complete. In any case, getting back to this, this was a use of mathematics that was quite abstract in terms of it wasn't exactly structured. You had a very real world kind of problem. And the one I really enjoyed was from a competition, and I called it Hurricane Higo because it gave us some sample data of power outages following a storm, and it looked like data that would have come from Hurricane Hugo, which hit in, I think, 1989. And we had to figure out an algorithm or something in order to decide how to send out repair crews following a storm. Figuring out sending out the repair crews, we came up with an algorithm and a program. We knew that you couldn't optimize just on the data we were given, because the whole point is this is sample data. We need to figure out some kind of heuristic or algorithm for future incidents. That's the whole point. We came up with a metric that looked at terms of cost and money to the company, the amount of time to get everything repaired. And then we came up with some kind of customer satisfaction metric based on the number of people affected, as well as the type of building that was affected. We came up with a program that kind of made some random data, and in terms of, ran some simulations and came up with some, rules of thumbs and heuristics, and that was our presentation. And we came in the top 15 solutions, my team. So it's a team of 3 students. We work over a weekend working on the problem. The thing is, the other team at NCSSM that year was in the top 3. In the top 3, they're the ones who get prizes, whatever the prize happened to be. And this is why. This was what was very, very funny. So we came up, we were trying to satisfy, it wasn't optimized, but like a good enough solution given some real world constraints. Well, these people were even more real world than we were, in terms of, they said, we're the electric company, we're a monopoly. We don't care about customer satisfaction, and we don't care about time. What we care about, we care about minimizing cost, and they won. So that was a very important lesson for me in terms of applied math problem solving in the real world for business. Every so often I come back and I remember I'm talking with somebody the next year about the solution they came up with, which was kind of technically true, but is not going to get you hired as a consultant. They actually went in and researched the cause of, repairing systems after blackouts, and saying, well, you actually need to know the network, otherwise you risk getting a brownout. And this is true. The thing is, we did not have enough data. So basically, they wrote a paper saying you can't solve it with the data given, which is not an answer for this kind of thing. So learned a lot from the class and then from the competition that he encouraged us to enter. I also did the competition the next year, but I was in college at that point when I did that. But I've gotten to do a lot of different kinds of math models before I've ended up in insurance-related stuff. I worked on a turtle population model, I remember. I worked on stuff involving speech quality evaluation, and in terms of software for use in drilling for speech pathology clients, so people who have to work on, say, reducing a lisp or reducing a foreign accent. And it's still difficult to do, because the kind of things that will flag something like saying yellow instead of yellow, they're very slight. If you do Fourier transforms stuff, they're very slight in time, and so they're very wide in spectrum, versus vowel sounds, which go ah, which has a lovely Fourier transform. Anyway, that's getting into that kind of crap. And I got to work on a patent dispute once as an expert witness. I've gotten to do a lot of interesting applied math related stuff. It's great to have a very broad toolkit in terms of math techniques and the kinds of math problems you can solve, but also understanding you need to solve these in real time. An algorithm that takes 2,000 years to complete is not a workable solution. You have to come up with approximations. So I learned a lot about, trying to do those approximations, simplifying problems, and making it work. It's like the Project Runway of math, I guess. Anyway, here's to Mr. Teague and showing me the world of applied mathematics.